Welcome to a new test and teardown video. This time it's a Grundig and also the H&B logo as you see there. So they joined forces. That is the Hartmann and Braun logo, by the way. And this one is a WobbelSender model 6016. It's from about 1956 to 1960, according to Radio Museum. It's tube based, so we got 5 tubes inside this one. It is about 15 kilo, so it's quite heavy. What can this do? Yes, we got 2 oscillators. One oscillator is over here, and you change the frequency here. And you got 6 frequency bands. The numbers here on the frequency bands is written here. So that will be all the different megahertz that this oscillator here can do. 4 to 250 megahertz. And then there's an attenuator of this output. Okay? So this is just an unmodulated fixed oscillator, right? You just put this and then how much you want. Then it is mixed to the output with the signal here, and you can also say how much you want from this oscillator. And this oscillator here is in one go, as you can see here. It goes all the way from 4 to 250 in one span using this one. So this knob here is called hop, but that is really how much it is jumping, how much it is modulating the width of the sweep. All right, and this width of the sweep also goes on the output here. So this is, you can use this on your oscilloscope for your X or your horizontal sweep on your oscilloscope. And this way you can sweep all sorts of filters. So that is basically the idea. And then the other here is for marker. So you have a little tiny little marker amplitude, and then you can adjust how powerful you want that and exactly where you want it to be. And this way you can accurately measure frequencies and such. So this could be used before a spectrum analyzer was a thing. I got a few problems with some of the knobs here. You can't really turn them, so I really need to open it. And it is also in a quite bad shape. It's full of nasty corrosion and dust and such, so I'm a little bit afraid of what we'll find inside. Here in the back, doubled fused input and mains voltage selector. I believe you pull this and then you can change the voltage. At the moment I think there's a tiny little 220 written in there, but you need a magnifier to read that one. And we got some so there's a crystal oscillator in here, and you can turn this on and off. And this is of course a very accurate frequency, and you use this to calibrate the variable marker frequencies, as you saw on the front. And that is of course, the nameplate says it's model 6016. Oh dear, this is really bad. This is exactly what I was thinking. Look at the fungus and I mean, let's try and touch this. This is some sort of, I don't know. It looks like somebody changed the cable, right? Look at that nasty. So this one was left outside in the rain. Look at that, completely corroded. And that is, what is that, a bird dropping or something like that? I don't know. But it looks really bad. That will be the 2 attenuators, by the way. This is a very used model back in the 50s and 60s. It's just a resistor potentiometer with double resistors in here. So it's a real attenuator. And they're quite good, despite the quite simple construction. and you'll see them in almost all electronics from this time. So here we got the tube covers, and this way you can access the tubes, and they have been sitting nicely inside here, and they're well protected. Look at that, nice and clean. So that is good so far. This is the yeah, that will be the fixed frequency. I'm mostly interested in the wobble part, the sweeper part, because in here we're gonna find a very interesting part. How are they doing the frequency, variable frequency control and the modulation for frequencies? I really look forward to show you guys this, if I can find that very special part they made for this. So, oh yeah, look at that up here. This is falling. Ooh, look at that. If I touch this, I'm gonna show you how. Oh, see? Just a tiny little gentle touch, and then it falls apart and goes to dust. So this is really important to remove all this. Otherwise I get all this nasty sticky dust all over the place. And there's another little problem I can see here. I don't know how visible this is on the video, but this whole plate here, there's a little bit of glitter. If you look around here, can you see the glitter? Those are tin whiskers that shines and reflect in the light. So that means this surface treatment of this metal box is just full of tin whiskers, and they go like 5-7 millimeters up in the air. So that means they will also be on the inside, and they short all sorts of stuff and create all sorts of problems. And they are also on the other part here. Yeah, that is definitely a problem. Whew, I was outside cleaning most of all the dirt away, and I'm still running my inspection round to figure out is there any way that I can repair this and get it up and running. See, here is one of the switches that is not possible to move at all, and I think it's because somebody tried to clean it using some of this nasty stuff that turns into green chewing gum. That's a little bit of a funny way this switch is designed. You can see the outside contacts on the rotary side like that. It's a little bit interesting to see the way that that is made. And that is of course the calibration oscillator, and the tube that is made for that part. Mains transformer is of course easy to locate, and we got some melted down, blown up capacitors around here. And also this resistor here looks like there has been some sort of a meltdown in this area, so that is not too good. Also, when I move this around, I can hear some loose parts, so try and listen if I do like this, okay? Oops. So there's a loose part in one of these compartments over here, so I think I will go in there and have a look. What else can I say about this? Yeah, I think we definitely just open these and have a look what is going on here. I see a lot of sign of corrosion, so it's probably also bad inside, right? Yeah, that will be the high voltage rectifier. So this is inside the broadband sweep generator. And yeah, the first thing you see, and that's exactly what I was already talking about before, the tin whiskers. Let's see if I can, yes, I can actually get them into focus. See the distance they travel, and that's like 5 or 6 millimeters of, yeah, just tin or some other, it's definitely electrically conductive, this material, and they can reach all sorts of stuff and create short circuits. And because many things in tube electronics is high impedance, so yeah, that is why it's creating all sorts of problems. In here, this is the first oscillator, and there's a tube down there. I don't know if we can see the socket. The cool thing about this type of oscillator here, you see this little half circle at the down, all the way down. That is the output coupling, and it's center tapped to ground. So that means each of the two ends here, the outputs, that's a balanced output, right? And the other one here, the other half circle, that is the coupler to that inductor. So there's actually a whole centimeters of distance down to that coupler. So now the signal goes in here. And this is where all the magic happens. Unfortunately, they're using a fully potted transformer. And this is the secret, fantastic part. I should probably just show you on the schematic how that works, because it's explained really good in the schematic. There is a main input coupling winding on that transformer, and that is the red wire here that goes to the low frequency input. So in this case, it's actually mains frequency. And then there's a resistor to ground here. There's a little black one down there. And this winding here creates a magnetic field in a transformer that goes down to a tiny little ferrite. And that ferrite is coupled to a few windings of the oscillator. So when there's a strong magnetic field at the low frequency that goes into the ferrite, the more and more magnetic field, the less and less inductance you have in the ferrite, and that means you will tune your oscillator using variable inductance as a result of the magnetic field and as a result of the input current to that primary side of the transformer. So that is a pretty genius way to make a super wideband frequency modulated oscillator. Here's the fixed frequency oscillator. There's no modulation or anything here. We got 6 ranges. Let me try and dial the different ranges. At the beginning I was hoping for a carousel switch, but that is not the case here. As you can see, it's just the switch that rotates down there. We got the 6 different inductors and capacitors and all that kind of stuff here for the oscillation ranges. And it's really cool, connected with a chain. See, a chain drive down there. That is nice. And yes, here we go. So here is the normal frequency adjustment that goes into the capacitor here, and that shaft here is directly connected to the readout at the front. There, I also find a few problems here. Again, this type of capacitor here is sort of cracked and leaked. You can see some kind of 2 or 3 cracks you can see here on the side, and this is how they kind of short circuit, create a huge temperature, and then it spits out some sort of guts. And sometimes it just goes a little short blitz, and then the rest of the capacitor actually works. And sometimes they just do a complete meltdown and set everything on fire. You never know exactly how it's gonna be, but this one, it turns out to be quite nicely done. And you can obviously see the series resistor to that capacitor here has been overloaded during that meltdown. Normally they should look quite nice and intact like this. And I think they also use these capacitors on low voltage stuff. That will of course be the high voltage. There's a tube socket down here, and obviously the end of that tube socket is also the warmest place in here. You also have a nice warm resistor here, and this is of course why you see problems in this capacitor before the nice and cold capacitors, because cold stuff just tend to live longer. I also think I found the little loose part, and look at that. See, there's a set screw missing right there, and that is the type. And look down here. I don't know. Yes, there you are. That down there is the little missing set screw. This is just the impossible place to get light in. But you gotta believe me, there's a set screw down here somewhere. If you can only get out. Yes, here you are. And now I'm about getting myself ready to try and power this up. So I want to perform a little bit of maintenance here on the mains entry. I really want you guys to know this. In the old days, red is the protective earth chassis and all that. And then they could even do ground for live. And the black is of course also mains input, right? So be warned about this when you see a 3-wire cable like that with a red one. Be afraid and double check is which one of these is actually connected to chassis, and then you can mount your connector correctly. Otherwise you're definitely gonna get into problems. So here is my little power up attempt. I connected a spectrum analyzer, tons of attenuator on this one. I really don't want to blow it up again on some old crappy equipment. No way. And I adjusted both of them. This one for, I think, 20 megahertz. This one 30 megahertz. And yeah, I think everything here should be quite all right. My idea is to turn this on and slowly crank up mains voltage, while I, of course, monitor the mains usage. But also with a thermal camera, I will monitor the temperature on capacitors here and this cracked capacitor here. Because if all 3 capacitors, they run cold, then I would like to continue and see if everything is working. And if they get warm, you know, it's easy to figure out if I need to repair them or not, right? They do look a little bit spooky, right? Let me just show you this real quickly. I got about 100 volts of mains incoming voltage, right? But look at that resistor here, it's 200 Celsius. So, and none of the capacitors there getting warm. So I bet we have yeah, nothing is warm in here, so this is just my own reflection. This reveals that we have a shorted voltage somewhere. So here is a really good trick for you guys who wants to repair old tube stuff. Of course, the high voltage is about 300 volts, right? Or 200 or 300, something like that, right? So when you have something that is shorted like this, you can crank down your mains entry with a variable transformer. So I'm just using 33, whatever it is, low voltage input. And the anode supply voltage is actually also in this range. So if I measure the incoming voltage, see, it's also 33 here on the right side of that resistor. So this is a filter drop resistor to the capacitors. And then I measure the other side of that. Oops, 0.0. So we have a high voltage rail short. And it can of course be some of the capacitors. It can be almost anywhere. But that is definitely where we are at so far. About this resistor, it's called R36. It's very easy to find on the schematic, and of course it's super easy because they're using really special values for many of those resistors, so that means they're super easy to identify. So that has to be R36 because it's 2.5 kilo ohms. So at the left side we have the full anode voltage, but on right side we have 0 volts. So is it that capacitor C51 that is shorted to ground, or if we follow that line from C51, then you can see it goes via a filter into the oscillator part, and inside the oscillator part you can of course also have a capacitor shorted to ground, and also that filter could be shorted to ground. But normally you don't see those 2 nanofarads filter parts there. You normally don't see those shorted because it's very low values and there's no current or no AC ripple current or anything like that heating up those filter capacitors. So it's really not likely to have a short there. Also, there will be an inductor inside that filter. So that means if there's a short inside the oscillator part, you will have a little bit of voltage drop over that filter inductor. But we measure 0 volts, so that is why I definitely want to attack C51 first. So it's quite easy to figure out what is going on in a system like this, because you can see one capacitor down there is connected to the good side of that resistor, and then the left side, this is where we have 0 volts. There's a wire that goes to this resistor, and here there was a wire down to that capacitor down there, and it was connected here. So I just disconnected C51, and now we'll measure if we got the voltage. Let's just turn on my 33 volts. But now I got 8 millivolts. So that is interesting. That means it's not entirely that. That is interesting. Let's look on the right side. Ooh, maybe this resistor is broken or something, because now it's nothing. Ah, see, there's also a little wire down here going somewhere. So this can be loading it. Here's 10K, so this can't really load it, right? Aha! So here we go. That capacitor here is definitely working. You can even measure it's 50 microfarads. So I follow this red wire, and it goes up here. It's connected together to that. It goes down, and it looks like it's connected to that filter inductor, but that is not the case. They just use this to hold the wire, and then the wire goes down below here. That will be the entry filters to that box, and number 2 here is the high voltage entry to that box. And inside this box we got one more of these fantastic capacitors up here. I disconnected that one, and this is the short, not the filter components, but that capacitor here. I'll try and see if I can get this out so I can show you. It's definitely cracked a little bit. Well, this is really difficult to see. But there you have it. Sometimes it's not super visible on these capacitors. You can see here it's shorted. But it's not... I mean, that is a tiny little crack. But it's not really a lot. And this one didn't melt down or anything like that. Alright, now I can continue. It says 250 volts. So I look a little bit forward to see how much we really got in this location. I can't wait to show you what is going to happen. Haha! I got my high voltage on the left side. And it just goes up and up, and I'm still powering it with 33 volts, and it's not pulling any current. I think I will continue now and see what happens, and I will of course monitor the rest of the capacitors with my thermal camera, so I need 2 hands to do that, unfortunately. So we're running at 220 volts input. It's using about 50 watts, and all temperatures on all resistors, they are about normal. 120 Celsius for the warmest one. This is just how it is. Still looking for any warm capacitors. And I think the capacitors here, they get warmed up by the resistors right next to them. And this is what is causing this. Oh, there's an... Oh, see? Did you see that? This is not so good. There was a nasty smell coming out of the potentiometer. Oh, yeah, poo, yeah, poo. They made it real easy for me to debug this, because they wrote inside the chassis R32 near that potentiometer that burned. So if we look at the schematic here, so if R32 can burn, that means something else needs to be bad, right? It cannot be anything connected to R37, because again, the resistor values are 30 and 31. Those are quite high, right? So it can only be C48. That is shorted. So I have to go and figure that out. There are many things I don't understand in this world. The first one is, why are we having that high voltage out of the transformer that goes to the two 30K resistors, and then the voltage goes to the output, the horizontal variable horizontal for your scope. And then what is this capacitor doing? The 50 nanofarad capacitor, it's connected here, and then it goes to the potentiometer here. There's no way this is doing anything good. And of course, when it's shorted, you get way too much voltage into your potentiometer R32, and then it melts down. And this capacitor here is, of course, really close to burning hot resistors. And I don't understand the whole concept why you want that high voltage out to your horizontal trigger of your scope. I mean, are you driving the deflection directly, or what is the purpose of this? I can of course back this up with a measurement. That will be the output from the transformer to the two 30k resistors. And now I just crank up my mains voltage again. And this is, let's go all the way to 220. I have now reached 220. So we got 200 volts coming out of the transformer to those two 30k resistors. It's not a big secret surprise they get warm, right? And of course this capacitor is broken, and then it blows up R32. I mean, this is quite stupid. But anyway, what I can show you, we got output. And the reason why this comes and go, I think it has something to do with the width of the modulation. But let me set this up. I'm sorry the unit is upside down because I'm measuring some stuff up here. But I think you get the point with the spectrum analyzer. What I'm showing here is, this is the wobble part of it. Here's the attenuator for the wobble part. And if I turn this like that, yeah, then you can see this is the carrier. For some funny reason, it just goes on and off all the time. It is completely unstable. So I haven't yet figured out what is causing that problem. Well, it's probably another capacitor that's going to blow up in a minute. And here is the marker oscillator. See, it's that one. And this is nice and stable, and yeah, you can completely play with that one. And this is, of course, the frequency for the marker oscillator, and all that works perfectly fine. We've got different bands. See, click, another band. And all those bands seem to be working quite all right. So we got a nice marker oscillator here. And yeah, you can turn on and off the marker oscillator and give it quite a lot of drive. And let's turn off the marker oscillator, just crank it down right here. So here's the wobble oscillator that for some reason goes on and off so far, but just pretend that it is always working, right? Then here is they call this hub, but this is of course how much drive. Let's crank it up. So here's now, yeah, give it, that's a little bit of context stuff. So now what you see here is the wobble oscillator going absolutely maximum modulation. And let me, yeah, I want to go down in the area here where we can see what we're doing. Isn't that fantastic? So now it's doing its thing, and I think it is a little bit more constant now, isn't it? It's not going on and off and all that. And the reason why it's looking like it's sweeping here, it's because my analyzer is just in free running mode, and this output here is jumping to the mains frequency. So what we see here is actually just a scan interference kind of thing, and then it looks like that. This is of course not how it is in real life, right? So yeah, I think that is what I wanted to show you about this fantastic old wobble generator. And it was fun to get it up and running. Got some nice and beautiful light in it and all that kind of stuff. There's still a few days of cleaning up and figuring out how to repair all the different capacitors and little minor details here. But anyway, I think that is what I wanted to show you. So thank you very much for watching. Bye bye.